Okay. So welcome everybody. Our first lecture is on polynomials. Before we get started with the lecture, I'd like to just mention a few things. So if you haven't already, please check out the handout that's on our website, and it'll help you guide you through the lecture. So it's basically most of the stuff that's presented in the lecture, but you have a copy of it. And if you looked at it beforehand, you'll know a bit of the basic stuff that we're covering first. So first, let's go over some definitions. A polynomial is an expression of the form f of x is equal to a sub n times x to the nth power plus a sub n minus 1 to x times x to the n minus 1 power, so on and so forth, until plus a sub 0 times x to the 0th power, which is 1. So it's a constant term. And we call the a sub 1 through a sub n, a sub 0 rather through a sub n, they're all coefficients. And a term is each one of the summons. So each one of the terms that look like n times x to the n is a term, etc., etc. And the degree of the highest term with a non-zero coefficient is called the degree of the polynomial, and a sub n is known as the leading coefficient. And another special term that often comes up, especially in competition math, is monic or monic. And that just means that the leading coefficient is equal to 1. All right. So now let's proceed to some basic theorems. So 1.1 is called the division algorithm. So given polynomials f and g with rational coefficients, and g is not equal to 0, which means g, the function g of x is not equal to 0, there exists unique polynomials qr with rational coefficients such that f equals qg plus r, where the degree of r is less than the degree of g. Now, this theorem is just saying you can divide one function with another, and the remainder will have a degree less than whatever you're dividing by. It's a rather basic theorem, but it's just quantified here, put into math terms, so to speak. All right. For 1.2, we have the remainder theorem, or the factor theorem, which follows from the remainder theorem. So when you have a polynomial f of x that's divided by x minus a, the remainder is f of a. So more precisely, there exists a unique polynomial q of x such that f of x is equal to q of x times x minus a plus f of a. And this follows from the division algorithm. And you can try to derive this yourself on your own time, but because of time constraints, I will not be deriving it for you guys. Similarly, you can also derive the factor theorem from the remainder theorem, which means that the polynomial f of x is divisible by x minus a if and only if f of a is equal to 0, which follows directly from the above. And now we'll do the total of 5 theorems. So now the third theorem is the rational root theorem. So the rational root theorem, I don't know if you guys have heard of this before, but if we call the function p of x is equal to a sub n times x to the nth, so on and so forth, in other words, p of x is a polynomial where the coefficients, in other words, a sub 0 through a sub n are all integers, then if p of s over t is equal to 0, in other words, s over t is a root of this polynomial, then s is divisible by, or s divides into a sub 0, t divides into a sub n. So basically that means if you have a fraction, say s over t, and you have the leading coefficient a sub n, and you have the constant a sub 0, right? It's basically saying that s must divide into this, and t must divide into this. And this is somewhat intuitive when you factor, and we'll see this later. We'll see a possible reason why this is when we discuss Vietta's theorem later on. But for now, just remember that the numerator of a rational number that is the root of a polynomial with only integer coefficients, the numerator divides the constant, and the denominator of the root divides the leading coefficient. And this is only true if you, of course, simplify the rational number. Yeah, let's move on. So next we have 1.4 and 1.5. So the fourth theorem and the fifth theorem. So the fourth is actually a lemma. It's called Gauss's lemma. And if it says if a polynomial with integer coefficients can be factored as the product of two polynomials with rational coefficients, can be factored as the product of two polynomials with integer coefficients. Now this lemma rarely shows up, if ever. It shows up more in Olympiad and proof problems, but the essence of these lectures is mostly directed towards lower level, or rather not low level, but more like competition-based math, in which case proof, this might come up in proofs, but it won't really come up in competition in practice. So, and lastly, we want to know 1.5, the fundamental theorem of algebra, which basically just states a non-constant polynomial with complex coefficient has at least one complex root. So yeah. All right, now, so one thing that comes up a lot when you start or introduced to polynomials is the concept of factoring. And I'm sure that if you're in 8th grade, you might already be introduced to this concept of factoring, factoring quadratics, factoring polynomials, so on and so forth. Right. So for the next section, we'll be reviewing common techniques for factoring and also some examples. All right. So first, let's see. So obviously, I think if you're acquainted at all with composition math, you should know these three factorizations, right? So the first one is commonly known as the sum of squares, or square of sum, and then this second one is the square of differences, and the second one is a factorization for the difference of squares. And if you are acquainted with combinatorial notation, now don't worry if you're not, because we will be having a lecture on combinatorials, combinatorics, and similarly combinatorial notation later on. I believe it's lecture, I'll probably introduce the concept in lecture 3. The following theorem will be especially helpful towards solving problems involving polynomials. So it says for real or complex a and b in non-negative integer n, we have a plus b to the nth power is equal to the sum from k equals 0 to n of n choose k times a to the n minus k times b to the k. Now, this theorem, if you don't know what follows, is you can visualize it as Pascal's triangle in a sort of way, and there is a derivation for it. You can look it up, and if you're acquainted with competition math or higher level math, you might want to try to derive this theorem by yourself. So for example, it would mean that, say we want to do, let's do a really quick example. So we have, let's try to do x plus 1 cubed. This polynomial, the binomial theorem, if you don't know like what x plus 1 cubed is off the top of your head, you can use the binomial theorem. So you have a is equal to x and b is equal to 1 and n is equal to 3, right? So you have 3 choose 0 times x cubed plus 3 choose 1 times x squared. Sorry, x squared times 1 to the first power plus 3 choose 2 times x times 1 to the second power. So I guess it looks like a 4, but it should be a 1. And then it should be 3 choose 3 times 1 to the third power. So, if you evaluate this, you get that this is equal to then, this is equal to x cubed plus 3x squared plus 3x plus 1. All right. So that is just how you would apply the binomial theorem in practice. Like, and you'll get more used to it as you do more problems. All right. So let's move on to another special technique that often comes up in factoring, and it comes up so often that we have a special name for it. It's called Simon's favorite factoring trick. And these problems most commonly involve an expression in the form xy plus ax plus by plus n, and you can factor it as x plus a times y plus b plus the constant n minus ab, which is equivalent to the above expression. And this often shows up because it commonly shows up in problems, especially asking for integer factors, because what happens is you can move this n minus ab to the other side, right? Because you set this expression equal to 0, you move the n minus ab to the other side, and then it just becomes a question of finding factor pairs, right? So let's look at an example of Simon's favorite factoring trick. So it says, find 3x squared y squared if x and y are integers, such that y squared plus 3x squared y squared plus 30x squared plus 517. Now, at first glance, it might not seem that this problem requires Simon's favorite factoring trick, but because it doesn't look like the expression above. But you'll notice that with a simple substitution, we can let a equals x squared and x equals x squared and y equals y squared, right? So it doesn't have to be x and y specifically. It just has to be some expression in that form. So first, what we should do, sorry, let me get someone in. All right. Oh, sorry, let's keep on going. Right, so first we have, first we can move the x squared term to the other side, right? So we have 3x squared y squared minus 30x squared plus y squared is equal to 517. And what we can do then is we can do 3x squared plus 1 times y squared minus 10 plus 10 is equal to 517. So if you notice, we basically applied Simon's favorite factoring trick, but instead of x, we used 3x squared, and instead of y, we used y squared. And you can see how this can be very helpful, right? Because in the beginning, what would you try to do, right? Like, you might try to brute force this problem, but you can see that with a clever factorization here, you can essentially reduce the problem to finding factor pairs, because it mentions specifically that x and y are integers. So this is the key part, right? So after factorization, we find that 3x squared plus 1 times y squared minus 10 is equal to 507. And then the factors of 507 are, so 507 is equal to 3 times 13 squared, right? So first of all, we know that 3x squared plus 1 can't possibly be a multiple of 3, and 169 doesn't work either, because if you try 169 equals 3x squared plus 1, it does that x won't be an integer as it's in the problem. And so then clearly 3x squared plus 1 has to be 13. So if 3x squared plus 1 is 13, then x is equal to 2, right? And that means y squared minus 10 is equal to 39, is equal to 39, and that means y equals 7. Sorry, y equals 7, right? And then lastly, we want to go back to the problem to make sure we're finally finding the right thing. It asks for 3 times x squared times y squared. So 3 times 2 squared times 7 squared is equal to, give me a second, is equal to 588, all right? And that's our answer. So you can notice that this problem was simplified greatly just by us using Simon's favorite factoring trick. You'll notice that the constant term doesn't have to perfectly factor into Simon's favorite factoring trick for this to be applicable, because as you can see, there was a 10 term, there was a plus 10 that we had to correct for, but or sorry, the minus 10 constant term that we had to correct for. But we were able to determine what 3x squared plus 1 and y squared minus 10 multiplied to. And because we know that x and y are integers, and then this becomes a problem of finding factor pairs, which is significantly easier than, say, trial and error. So that's what makes Simon's favor factoring trick so useful. All right, so now let's do some more examples of factoring. Right. So here we have the second example. It says, for certain real numbers a, b, and c, the polynomial g of x is equal to x cubed plus ax squared plus x plus 10 has three distinct roots. And each root of g of x is also a root of the polynomial x to the fourth plus x to the 3 plus bx squared plus 100x plus c. And then finally, what they want us to find is f of 1. All right. So what should we do here? Well, first, because we know that each root of g of x is also a root of the polynomial f of x, then we know that f of x is equal to g of x times some x minus r. And we know there's only, we know it's only a first degree polynomial, and the leading coefficient is 1, because g of x is of degree 3, and f of x is of degree 4. So that necessarily means the quotient is of degree 1, and the leading coefficients of both are 1. So that's why we know that the quotient is of the form x minus r. Next, what we can do is we can substitute and expand, right? So we get f of x is equal to x cubed plus ax squared plus x plus 10 times x minus r, which is equal to x to the fourth plus a minus r x cubed plus 1 minus ar x squared plus 10 minus r x minus 10r. Now we'll see that if we compare the coefficients of this expanded expression with the coefficients of f of x, we notice that a minus r equals 1, right? And we also notice that 10 minus r is equal to 100. So what this basically means is, what this basically means is, from this equation here, we know that r is equal to negative 90. And from this equation here, we know that a is equal to negative 89. Now, if we go back to our original expression, we know that f of x is equal to g of x times x minus r. And now if we plug in our values, right? So g of x was equal to x cubed. So first we notice that f of 1 is equal to g of 1 times 1 plus 90, right? Because negative r is 90. And then if we evaluate g of 1, we evaluate g of 1 is equal to x cubed minus 89 x squared plus x plus 10. This is equal to, right? So if we multiply, g of 1, evaluating x equals 1, plugging x equals 1 into this expression, and then plugging that into the expression for f of 1, well, from now on, it's just basic arithmetic, right? Like, can you plug in x equals 1, and it's 1, right? So it should be easy to plug in. So if after plugging this in and doing some basic arithmetic and some multiplication, we get that f of 1 is equal to negative 7,007. And this problem was actually, oops, if you look at where I sourced the problem, you notice that this problem was actually number 24 on an AMC 10, which is reasonably difficult for most of you guys here, right? So you notice that by simply using, you know, by simply dividing these polynomials and, comparing the coefficients, we essentially solve the problem very quickly. And you'll see this play out like over and over again, where each type of competition problem usually has some sort of trick or something, and they'll usually spin it in different ways, but the overall concept is the same. So in this case, it was recognizing that f of x is divisible by g of x, and then recognizing that it would be multiplied by some function in the form x minus r, right? And then finding a and r, a being the coefficient in the unknown g of x, and then r being the r value in the unknown quotient, and then we simply just had to apply what we learned, and then we would get the answer. All right, so let's do. I think we have 2 more examples. All right, so here's another example. Let p be the product of the non-real roots of x to the fourth minus 4x cubed plus 6x squared minus 4x equals 2005. And here, what comes in handy is the binomial theorem. So let's suppose that you don't know the expansion of, let's suppose you don't know the expansion of x minus 1 to the fourth. Now, experienced people with competition math will instantly recognize that the expression on the left-hand side looks really similar to the expansion of x minus 1 to the fourth. Now, if you don't know what that is, you can use the binomial theorem to evaluate it, but I'll just tell you what it is now. It's x to the fourth minus 4x cubed plus 6x squared minus 4x plus 1. So you notice there's just the plus 1 that's missing on the left-hand side. And we can account for that by doing the following. So Andrew asked, what is the binomial theorem? I think he came late, so that's maybe why you don't know. But if you look at the handout that's on our website, you'll notice it's just a way to expand binomial terms to a certain power by using a simple combinatorial trick. And I'll show the formula for a few seconds, so you can copy it down, or you can look at our handout. So I'll show it for a few seconds. Let me find it. I think it's here. Yeah. Right. So here is the binomial theorem here. Basically, it's just a way to expand a binomial expression to a certain power, and it's really helpful if you need to compute something on the fly, but you don't want to expand it step by step. All right. So where was I? All right. 2 point. Was it here? No, I was on another example. Here. Here. All right. Example 2.3. So let p be the product of the non-real roots of x to the fourth minus 4x cubed plus 6x squared minus 4x equals 2005. And it asks for this symbol just means, this symbol here just means the 4 of p. So that means the integer that is the greatest integer that is less than or equal to p. All right. So first we can add 1 to both sides and then factor the left side, right? So then we would get x minus 1 to the fourth is equal to 2006. And then basically what this means is that, all right, and then what we can do is suppose that we call And then what we can do is we can apply difference of squares. Actually, let's do this method. Right. So let's subtract 2006 from both sides, right? So you can get x minus 1 to the fourth minus 2006 is equal to 0. And then what you would, um, and then what you would get is you can do a difference of squares. Now you notice that 2006 is not a perfect square, but for our interest, this is not, but that's not what we want to find, right? What we want to find is the product of the roots, right? So let's continue. Right, so then what we would do is we know that x minus 1 to the fourth is x minus 1 squared, right? Just basic properties of powers. So we would get x minus 1 squared plus the root of 2006 multiplied by x minus 1 squared minus the root of 2006 is equal to 0. All right. And if you think of each part of the product as a quadratic, well, we know that any square of a real number is equal to a positive value, right? So that means that, so for example, a negative number squared is still positive, and a positive number squared is still positive, and 0 squared is 0, right? So every square of a real number is always greater than or equal to 0. So that means that any roots of this expression here on the left side must be non-real, right? So therefore, the products of the roots are, therefore the expression is x minus 1 squared plus root, we want to know the product of the roots of x minus 1 squared plus the square root of 2006. Okay. And for now, we'll stop here, right? Because to finish this problem, we'll need to know something called Vieta's formulas. And we'll come back to this problem once we learn what Vieta's formulas are. All right. So we'll be coming back to this problem. So keep this problem in the back of your head. We'll be coming back to it. All right. So let's do example 2.4 first. So this is a very hard, well, this is a pretty hard example, right? So we have example 2.4. We are asked to factor a minus b cubed plus b minus c cubed plus c minus a cubed. Now I'll give you a few minutes to, well, I'll give you like 30 seconds to think about how you might want to solve this problem, right? Because obviously, you don't really want to expand this expression because because most of the problems that I'm showing today do not really require a lot of brute force, but rather they use clever factoring techniques. So I'll give you 30 seconds to try to come up with a possible technique, or just think about any theorems that might apply when we try to factor this. Well, I'll respond to some questions. Um, and yes, this lecture will be recorded and it will be posted online as soon as we get it uploaded. All right, give me one more second and we can start. All right, let's get started. All right, so we can, okay, so this is a common technique when we factor these type of polynomials. So let's consider this as a polynomial in A, right? So suppose this is equal to some polynomial f of A, right? And if we, let's say we have A equals B, right? Well, then we have, well, then this term becomes 0, right? So then, and then we have 0, 0 cubed plus A minus C cubed plus C minus A cubed. And this is actually just equal to 0 because A minus C is the negative of C minus A cubed, right? So if we let X equals A minus C, then we have that this is X cubed plus negative X cubed, which is equal to 0. So then we can notice that, so therefore, we know that A minus B is a factor, right? This is just deriving from the factor theorem. And then by symmetry, we also know that B minus C and C minus A must also be factors, right? So if we call this a function in B instead, right? Let's call it G of B, right? Then we do something similar, right? So we call B equals C, and then we would notice that B minus C is a factor. And we would also know that C minus A is a factor. So far, we have established that the factors are A minus B, B minus C, C minus A, right? So this is equal times K is probably equal to A minus B cubed plus B minus C cubed plus C minus A cubed, right? Right. And now, what we can do is we will compare the terms of the form A squared B, right? So, if you want to expand, A squared B, well, on this side, it would just be, on this side here, the A squared B term would just be, let's see, well, you would have a negative 3 A squared B term from this first cube, and you would not get an A squared B from anything else. And then from the left-hand side expression, you would only get A squared B once, right? Because you need A from this expression, A from this expression, and B from this expression, and it has a coefficient of -1. Right. So that means if this is -1 A squared B times K. So that means if the left-hand side and the right-hand side are indeed equal, that means K must equal 3, right? And therefore, and then we've solved the problem, right? And then we just have A minus B cubed plus B minus C cubed plus C minus A cubed is equal to 3 times A minus B, B minus C, C minus A, right? And you can also find that K equals 3 via other methods, right? You can find the term of B squared C, any term of that form. But the general idea is you find that K is equal to 3. Okay, so that was a very, that problem was probably the hardest to see the technique because we applied the factor theorem. We applied the factor theorem here, right? And this is factor theorem. And here we had to compare coefficients, right? So this was basically a 2-part problem. But the difficult part of this problem was first establishing and approaching the problem, right? I think a lot of people would have just chosen to brute force the problem. which I think could be viable, but at the same time, this solution, because it's a product of three binomial terms, right? That makes it a lot harder to find the factorization. And so it's important that you grasp the concept of, making the function in terms of one variable, and then maybe finding conditions such that that function evaluates to zero, and then from that, the finding like what are the factors, right? So that's generally how you use the factor theorem. And after that was just comparing coefficients. Don't make mistakes when expanding. Okay. Yes, this is algebra. All right. All right. Let's move on to one more important topic. We're a bit short on time, so I want to get through this, get through Vietas at least. So we have Vietas formulas. So Vietas formulas are a special technique that comes up very, very often in composition math. And basically, if you add the roots of a polynomial f of x is equal to a sub n x to the nth plus a to the a plus a to the sub n sub, so just the regular polynomial form with the leading coefficient not equal to zero, then basically if you group the roots and take their products k at a time, right? So let's call s sub 1 just means one at a time, right? So r sub 1, so the first root plus the second root plus the third root plus all the way, right? Another important distinction is that it doesn't matter if it's multiplicative. So if you have like two roots that are 6, then both of them count as roots, right? So that, for example, if we have x squared minus 2x plus 1, then you have a double root at 1, right? So then r1 would equal to 1 and r sub 2 would also equal 1. So that's an important thing to remember. So multiplicity does not mean that it's not included again. So we have, if we call s of 1 is equal to the sum of the roots, s of 2 is like the product 2 at a time, right? So r sub 1 times r sub 2, r sub 1 times r sub 3, r sub 1 times r sub n, all the way, right? All the way to r sub n minus 1 times r to the r sub n. And then finally, we have the final product, right? So s of n is equal to the product of all the roots. Then the polynomial a sub n, blah, 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 right? So the regular polynomial form can be factored as a sub n times x minus r sub 1 times x minus r sub 2, x minus r sub n, etc., etc. And when expanding, we find that f of x is equal to a sub n times x to the n minus s sub 1 times x to the n minus 1 plus s sub 2 times x to the n minus 2, etc., etc., right? So that means the sum of the roots is equal to the negative. So here, the most common ones are, you find that the sum of the roots, so the sum here is equal to the negative of this coefficient divided by this coefficient. And similarly, then the product of the roots here is -1, right? Remember the -1 to the nth power, which is the degree of the polynomial, multiplied by a sub n, a sub 0, so the constant term over this, right? And similarly, you also get, the sum of the pairwise products of the roots is equal to well, it's not mentioned here, it's not written here, but it would be a sub n minus 2 times x to the n minus 2, right? And then we would have that the sum of the pairwise products would be equal to, well, -1 squared times a sub n minus 2 over a sub n. But, well, -1 squared is just 1, so we can ignore that, right? Oops, that is not what I meant to do. All right. Right. So essentially we have it summarized here, right? So this is the important takeaway, which is that the sum of the products of the roots taken k at a time is equal to -1 to the kth power multiplied by a to the n minus k. So the coefficient of x to the n minus k divided by a sub n, which is the leading coefficient. So now, if we go back to our problem before, we established we established that the product of the non-real roots of this expression here, so x minus the product of the non-real roots of x of this equation here are the roots, well, the non-real roots of this expression here are the roots of this expression in red, right? Right. So this is equal to 0, right? And now we just have to use Vieta's formulas, right? So if we expand, this is x squared minus 2x plus 1 plus root 2006. And we want the product of the roots. Now, what does Vieta's formulas tell us? Well, it tells us the product of the roots is equal to the constant term over the leading coefficient, right? So the leading coefficient in this case is 1, and the constant term is 1 over root 2006. And so that means that the product is just equal to this value. So it's divided division by 1. So we can ignore that essentially, right? And then finally, it asked us for, if we look back at the problem, we want the floor of P, which is the greatest integer less than or equal to P, right? And then the greatest integer less than or equal to 1 plus root 2006 is 45, I believe, because the 4 of root 2006 is 44 and then plus 1. So 45 point something some. So this is 44 point something something something, right? And then you add 1. So it's 45 point something something something. And then you have the 4 of that. So that's the greatest integer less than or equal to that, which would be 45. Right, so we established then that the floor of 1 plus root 2006 is equal to 45. And that's our answer, right? So you'll notice that this problem was a combination of both realizing a common pattern and then using that to factorize it, and then using a common factorization again, right? The difference of squares to factor it again. And then finally using Vieta's formulas to finish off the problem. All right. I think we have time for maybe 1 or 2 more examples. Okay. We have enough time, right? So let's erase that. I was testing something. All right. So let's start with a simple example. Let A and B be the solutions to x squared minus 3x plus 7. And we want to find a squared plus b squared. All right, so at first glance, we might notice that a squared plus b squared is not a value that is covered in Vieta's formulas, but we can do a little bit of clever algebraic manipulation, right? So a squared plus b squared is equal to a plus b squared minus 2ab. And we know how to find a plus b squared. We know how to find ab. So then we can just evaluate this, right? So by Vieta's formulas, the sum of the roots is 3, right? So 3, because it's the negative of this coefficient, the 3 coefficient, the coefficient of x divided by the coefficient of x squared, right? So that's negative of negative 3 over 1, which is 3. And then the product is equal to the constant, negative 1 to the power of the degree of the polynomial, which is 2. So negative 1 squared, which is 1, right? Multiplied by the constant term over the leading coefficient. The constant term is 7. The leading coefficient is 1. So negative 1 squared times 7 over 1 is 7, right? So 3 squared minus 2 times 7, which is negative 5, right? So yeah, this is actually pretty common. So they give you like a polynomial, they call the roots a, b, c, d, whatever, and then they want you to find some expression in terms of those roots. Sometimes the problems will add extra steps to make finding that more difficult. Okay. Right, let's try to do this last problem. Okay. Okay. This is a very hard example, so don't be afraid if you don't understand everything that I explain here. You can come back to the lecture recording and watch this again. So how do I make this go down? Okay. All right. So let's do this problem. Okay. All right. So we noticed that we have let a, b, and c be the roots of x cubed minus 3x minus 1 equals 0. We want to find 1 over 2 minus a plus 1 over 2 minus b plus 1 over 2 minus c. Well, we notice that clearly this problem wants us to use Vietas, right? They use the roots of this polynomial, and then they want us to find some expression using those roots. All right, so let us, oh, and yes, for the previous example, sorry, what was that? 3.2.1 here. Right. The previous example here, you'll notice that yes, you can use the quadratic formula, right? You can find a and b using the quadratic formula. However, you notice that Vietas is much quicker, right? Because if you use the quadratic formula, you get something like a plus root b over c, and then you have to, you have to add them, and then you have to square them, and then add them, right? So that's very computation heavy. Whereas you notice here, we just used a very clever shortcut. Instead of having to find the roots themselves. And you'll see that's a pattern when doing Vietas. Rather than finding the roots themselves, you can find expressions for the sum of the roots or the sum of the products, pairwise products or something like that, and use that to find the value of the expression rather than finding the roots and then plugging those values into the expression. So this is the last example that I think we'll be doing today. And we have this problem here. We have let a, b, and c be the roots of x cubed minus 3x minus 1 is equal to 0. And we want to find 1 over 2 minus a plus 1 over 2 minus b plus 1 over 2 minus c. So we have that, well, okay. We have that this quantity we want is symmetric, right? So Vietas, first of all, we notice that this is symmetric, right? So that means like if we swap b with abc with like cba, right? We swap the permutation, the expression is still the same, right? So it's a hint. It's once again another iteration. So this first sentence here should be inclination that we should use Vietas. And the second here is that this is symmetric, right? Symmetric is an inclination we should use Vietas, and roots is another one, right? Using the roots to find, evaluating an expression that involves the roots of the polynomial, right? Oops, that's not what I meant to do. All right. Okay. So let's do this problem. Well, we want to find 1 over 2 minus a plus 1 over 2 minus b plus 1 over 2 minus c. And now, as much as I hate to say it, this problem is actually quite computational because we will be bashing out this expression. So yeah, this is another part of algebra. Don't be afraid to bash. Sometimes you might think that there's a clever solution, but sometimes you just need to bash. And bashing just means like doing a lot of computation to get a complicated expression, but eventually it'll simplify with a lot of computation. But yeah. So unluckily, this problem does involve some form of bashing, right? So let's put this over a common denominator first. Right. So let's zoom in. Oops. Let's zoom in and just grind away at this expression. Okay, so this is the expression here, and let's just put it all over a common denominator, right? So the common denominator is 2 minus a times 2 minus b times 2 minus c. And the numerator is 2 minus b times 2 minus c plus 2 minus a times 2 minus c plus 2 minus b, 2 minus b times 2 minus a, right? And then we have, well, from this expression, we get that this is equal to, right, 4 minus 2b plus c plus bc plus 4 minus 2a plus c plus ac plus 4 minus 2a plus b plus ab. Right, this is all over 2 minus a, 2 minus b, and 2 minus c. I apologize for my bad handwriting. I'm using a stylus, but it's not very effective. And let's continue bashing, right? So then we have 12, right? The forms from each of the three expressions, right? And then we have 2b's, minus 2b here, minus 2b here. So And then we have, right, so we have minus 2a here, minus 2a here, right? Sorry, you can't see where my pointer is pointing actually. So we have minus 2a here, we have minus 2a here. We have minus 2b here, we have minus 2b here, and we have minus 2c here, and we have minus 2c here. So you notice that in total it's minus 4a, minus 4b, minus 4c. And we can write that into the expression as minus 4 times the quantity a plus b plus c, right? And finally, we have plus AB plus BC plus AC, right? And we notice that we can find A plus B plus C, the sum of the roots, and AB plus BC plus AC, the pairwise products of the roots, very easily just from Vieta's formulas, courtesy of Vieta's formulas, rather. So now let's keep on going, right? We have 12 minus this 4 times a plus b plus c plus ab plus bc plus ac all over this expression again. So 2 minus a, 2 minus b, 2 minus c. And now let's finally get working on the denominator, right? So the denominator here is 12 minus 4 times a plus b plus c plus ab plus bc plus ca all over, this is 8 minus 4. Now you can check this yourself. I'm skipping a few steps here for the sake of time, but you can check this yourself if you wish. Just expand 2 minus a times 2 minus b times 2 minus c and see if you get the same expression as I do. So plus 2 times ab plus bc plus ca minus abc. Right. And we notice that we can find a plus b plus c, right? We can find a plus b plus c. We can find ab plus bc plus ca. And we can also find ABC, right? From Vieta's formulas. So now it just remains to plug it in, right? So we look at the original expression here, right? So the original polynomial so A, B, and C are the roots of this polynomial, right? So let's put it here in red, right? The polynomial is x cubed minus 3x plus 1, right? So we know that A plus B plus C is equal to 0. We know that AB plus BC plus CA is equal to -3. And lastly, we know that ABC is equal, oh my god, that's sloppy. Fix this too. A plus B, this is A, B, C is equal to -1. Oh, sorry, it's equal to it's equal to 1, sorry. It's, yeah, I'm sorry. I copied this expression down wrong. So this is -1 and this is +1, right? Yeah, so you can see that even I make these kind of mistakes. Make sure to go back to the problem. Make sure that you're always using the right expressions, right? Right. So now that we have these values, right? Now we have the expression, and now that we have the values for a plus b plus c, and we have the values for AB plus BC plus CA, we have the value for ABC, right? And this is all courtesy of Vieta's formulas, right? So you can see how helpful Vieta's is, right? Because imagine if you had to first of all, find the roots of this cubic. You say, for example, using the cubic formula, but I don't even think this one is, I don't think you can really do that by hand, honestly. And then you'd have to plug that into 1/2 minus a plus 1/2 minus b plus 1/2 minus c, and just be a lot of computation, right? It'd also be a lot of work to find the root of the cubic in the first place, if it is even possible to do by hand at all, right? Like it might be non-real roots. So clearly you can see how helpful Vieta is right now, right? So if we plug in these values, we get 12 minus 4 times 0, so 0, plus AB plus BC plus CA, so that's -3, over 8 minus 4 times 0, so 0, plus 2 times -3, plus 1. Sorry, -1. Yeah, so this is why it's important to always make sure your signs are clear. So -1. Right. And then we just evaluate this fraction, simple arithmetic. This is 9/1, so that's 9. And that is our final answer. So yeah, this problem involved a lot of bashing, right? So it might have looked really hard in the beginning if you didn't know Vietas, right? Because then you would first be stuck on how to find the roots, and then second, you would not want to plug those roots into the expression. But with Vietas, you know that first. Maybe you can manipulate the expression into uh, some sort of expression that you can find with the help of Vietas, right? So with Vietas, you can find the sum of the roots, the pairwise product, etc. So you want to get the expression in a form where you can plug in those values, right? So for example, uh, our last expression here would be one where we can use Vietas formulas to plug in values. And so you can clearly see how helpful Vietas was. So before we end, just a few things. Our handout is on our website. You can look up sites.google.com/view/DONLS for Descartes Online Math Lecture Series. In the handout, we both have the problems, the examples that we discussed today, although we don't have the solutions. But you can look at the solutions by looking at our lectures, which will be posted as soon as possible. We also have um, additional problems. Those that are completely optional, but we do recommend that you try them. And some of them are very difficult, so don't be discouraged if you can't get some of the problems. And we will be posting a solution set to those problems um, before the next lecture, which is on Saturday from 10 to 11 a.m. So thank you everyone for coming. If you have any questions or about whether it be about the course, whether it be about the lecture series or any comments you might have or like the curriculum, you can stay after. But for now, I will end the recording.